Hello and welcome to lecture number 10 in the course Advanced Robotics. In the last class, we talked about singular value decomposition and we also discussed about the Jacobian. And we said that there is a relation between the end effector velocity and the joint velocity that is related by the Jacobian. And then we also found that the singular points are defined as points where the determinant of the Jacobian J becomes equal to 0, which basically means in the physical world that if you want to go to a singular point, you require infinite energy in terms of the motor. Now, today let's discuss a little bit more in detail about the Jacobian and singularity. And let us look at a few metrics that are there, which actually indicates the ability to move in a particular direction in space. Now, what does that mean? It basically means that in my whole workspace, say for example, in my whole workspace here, I can move at every point. But as I start going near the singularities, what happens is that the amount of energy required becomes higher and the ability to move in a particular direction gets restrained. Now, what do I mean? For example, if you're going towards the end of the workspace, then what happens is that you will not be able to move in all directions equally. Okay, and so there is a metric, and this metric which is called the manipulation ability. Now, that's one point. The second is that when we are talking about, I gave the example of a 2 degree of freedom manipulator. There was only 2 joints and the Jacobian was 2 into 2, which is a square matrix. But suppose you have 3 degrees of freedom, 4, 5, 6 degrees of freedom of a planar system. In that case, what happens is that you have only x and y because it's planar, but you have 3, 4, 5 degrees of freedom at the joints. So your Jacobian will not remain square anymore. In that case, how do you find the inverse of a non-square Jacobian? Okay, now there's something very interesting. Suppose in the human hand, if you consider my hand, okay, so on the human arm rather, so there are 7 degrees of freedom. There are 3 degrees of freedom in the shoulder, 2 at the elbow, and 2 at the wrist. So that makes 7 degrees of freedom. So this is a redundant manipulator, which means that the Jacobian of this manipulator, that is my arm or your arm, will not be a square matrix. It will be a non-square matrix. Why? Because in 3-dimensional space, we have 6 parameters, you know that, okay? Whereas we have 7 joints. So if you look at the Jacobian, it is 6 by 7. So if I want to find the inverse of a 6 by 7 Jacobian, then what do I do? Now, something more interesting happens there. For example, if I am at a particular point in space, let me put my hand here, okay? And so this arm has 7 degrees of freedom. Now, suppose at this point in space, I have some xy, okay? And there is a corresponding theta 1 to theta 7 on the other side, okay, which is if I actuate them, then this joint should move. But there is a case here where I'm keeping my hand here and I'm moving my other joints. I'm moving the wrist, I'm moving my elbow, I'm moving my shoulder, but this point is not moving. So it's like saying, where did the energy go? Where did that velocity go? I was moving my shoulder, but my wrist is not moving. You can see that very clearly here, right? So wrist is still fixed at that XY point, but my elbow and my shoulders are moving. So in a redundant manipulator, there's something interesting that happens, that you can actuate a joint, but that joint motion need not be transferred to the end effector. Then the question comes, where did this velocity go? Where did the energy go? Okay, and this happens mainly in the case of a non-square Jacobian. Okay, so today let's look at a very useful tool that is used to study the properties of a matrix, okay, like a Jacobian, which is called the singular value decomposition. So today we'll talk about singular value decomposition and then we'll proceed. So let me explain the need for singular value decomposition, which gives us a better understanding of a linear transformation or a linear operator. Now, I'll very briefly talk about what we discussed in the last class, that we talked about singularities and the Jacobian, and then we'll proceed. So in the last class, we talked about the singular value, not singular values, but the singularity. Okay, so this was a 2-link manipulator, and we talked about the Jacobian. XY is the end effector position there, and there is two variables, theta 1 and theta 2. This is link length L1 and L2. And we said that in this particular case, we can write our equation x is equal to L1 cos 1 plus L2 cos 1, 2. And we can write y is L1 sin 1 plus L2 sin 1, 2. Okay. And then what do? We take the derivative of this, the partial derivative. There are 2 variables here, theta 1 and theta 2. So what we can do is we can take the partial derivatives of this and we get our dx is equal to minus L1 sin 1 minus L2 sin 1, 2. and minus L2 sine 1, 2. Then dy is equal to L1 cos 1 plus L2 cos 1, 2, and here it is L2 cos 1, 2. Okay, so in matrix form I can write it this way. Okay, d theta 1 and d theta 2. Okay, now this is called the Jacobian. Now in terms of control of the manipulator, every joint is connected with a motor. Okay, it is actuated by a motor. So I give some velocity input, the joint rotates. If the joint rotates, theta 1 will change, and if theta 1 changes, then xy will change. Okay, so it is like saying there is some relation between the joint velocities and the end effector velocities, and that is given by this relation which we discussed in the last class, which is x dot is equal to j into theta dot. Okay. Now j is a 2 by 2 matrix in this case. Okay. Now in terms of control, what is more important is that we want a desired end effector trajectory or end effector velocity, and I'm going to give a corresponding joint velocity. So what is more important is theta dot is equal to j inverse of x dot. Okay, now so what I need to do is figure out find out the adjoint of j divided by the determinant of j into x dot. Now we see that determinant of j comes in the denominator, so we say that wherever the determinant of j becomes equal to 0, we say that these points are singular points. Okay, that means the determinant of j is going to 0 means your joint velocity is going to infinity. So obviously it cannot go to infinity, it cannot even go anywhere near infinity. Now let's try and understand this a little better. Now what I'm trying to say is that this is a two-link manipulator. So depending, this is the work volume, let's say it's a circle. So depending where it is in that circle, the energy consumption is going to go up or go down, and the number of solutions will also depend on where it is. Say for example, if it is here, okay, this is the end, this is the end, okay, the boundary singularity here. So this is my boundary singularity. Now in this particular case, the manipulator can move very easily this side, but it cannot move this side. You can imagine this condition that your hand is fully stretched. You can move the hand up or you can move the hand down, but you cannot move the hand towards your body. In this direction you cannot move. Okay, so this means that velocity can be obtained. Okay, so we can move in a particular direction easily or not is governed by the Jacobian again, determinant of the Jacobian. Okay, because this is basically leading towards the singularity. Okay, so it is like saying that this is a singular point, boundary singularity. These are all boundary singularities. So when the manipulator comes there, the manipulator can move this way very easily, but it cannot move towards the center very easily. That means the ability to move in a particular direction is also governed by the singularity now. Okay, now what does this basically mean? Okay, so it basically means that if you have, let's look at this example here. We have a multi-degree of freedom manipulator. Let's say there are many degrees of freedom. Okay, there are many degrees of freedom here. This is my point xy, and we have theta 1, theta 2, theta 3, theta 4, theta 5, theta 6, and theta 7. Okay, so xy now is a function of theta 1 to theta 7. Now this means that suppose I have the same relation x dot is equal to j into theta dot. This j is now 2 into 7. It is not a square matrix anymore. Okay, now what does this mean? This basically means that if I can keep the end effector here, I can move some of the joints like this, like this, like this, like this, like this, and the end effector can still be there only. That means I give some joint velocity here, I give some theta input here in terms of joint velocities, but there is no output, there is no x dot or y dot here. So I'm giving input theta dot, but there is no output in terms of x dot. Okay, this is a strange situation, that the joints are moving but the end effector is not moving. So where did the velocities go? Because this relation is a relation between the joint velocity and the end effector velocity. Now in this case I'm giving joint velocity but the end effector is not moving. So where did that velocity go? Okay, now this happens in the case of redundant systems. Okay, That means the ability to move in a particular direction, okay, is also governed by this determinant of j. And if you're going towards the singularity, you're losing degrees of freedom. Okay, losing degrees of freedom to move. Okay, because you can probably move only in one direction but not in other directions. So if I'm in the center of the workspace here, I can move very easily in all directions. Okay, I can move in all directions. Okay, and that is where my maximum determinant of j for this manipulator was sine theta 2. Okay, so in the center of the workspace, theta 2 is 90 degrees. Okay, and that is why your determinant of j will become equal to 1, which is the maximum value. Whereas on the boundary here, your determinant of j will become 0, right? Because theta 2 becomes equal to 0. So determinant of j is equal to 0. So it means that there is a metric which is going from 0 to 1 as you are moving from the center of the workspace towards the boundary of the workspace. Let me say this again. Well, let me explain this concept of manipulation ability. So the term is called manipulation ability. So manipulation ability or manipulability is called, which means the ability to move in a particular direction. Okay, now let me explain how it is related to singularity. So I have this manipulator like this. Okay, on the boundary, when it becomes straight line, okay, it comes there. In that case, it has only one solution in terms of theta 1 and theta 2. There is only one solution. Okay, and it is in singular configuration, and this is called the boundary singularity. So what is the meaning of boundary singularity? It basically means determinant of j has become equal to 0 because theta 2 is 0 now. Okay, so theta 2 is 0 in this configuration. It is in singular configuration. In terms of solution, what does it mean? It means that only one solution is there. Normally a 2 degree of freedom arm will have two solutions, right? But here it only has one solution. Okay, now if the manipulator is somewhere in the middle of the workspace, let's say I bring it down here and it is here in the middle of the workspace in this region. Okay, in that case your theta 2 is 90 degrees, and theta 2 is 90 degrees means determinant of j is equal to 1. Okay, provided that L1 is equal to L2 is equal to 1. Okay, because determinant of j is equal to L1 L2 sine 2, right? So I'm saying that L1 L2 is equal to 1, so it depends only on this, and maximum value is when theta 2 is equal to 90. Now what does this physically mean? This physically means that the robot can move in any direction easily or equally well. Okay, whereas in this case it can move like this, but it cannot move like that. In terms of solutions, what does this mean? This means that there are two solutions. Okay, so in this configuration and this configuration there are two solutions now, whereas when it was stretched out there was only one solution. So there appears to be a relation between the number of solutions and the value of the determinant and singularity also. So when it is going to a singular configuration, it is losing the number of solutions and it can move only in particular directions, whereas if the determinant is maximized in the center of the workspace, then it means it can move in any direction equally well. Okay, so this metric is basically what we call manipulation ability, and is defined by W is equal to determinant of j. Okay, for a non-redundant system. Okay, now for a redundant system, W1 is equal to determinant of j transpose, square root of determinant of j transpose. Okay, this is for a redundant system and this is for a non-redundant system. Okay, so now we understand very well, we understand that there is some relation between the manipulation ability, the determinant, the singular values, okay, and the ability to move in a particular direction. So that brings us to the very general question that, okay, this was one, the relationship here. Now what I just talked about some time back is regarding the redundant system here. Another thing, interesting thing was happening is that in this particular case, you're giving an input. That means I'm giving joint velocity, but there is no end effector velocity. There may be, there may not be. Okay, because I can rearrange these links in such that this joint does not move. So where did the velocity go? Okay, so these are interesting things that happen, and to study them, we basically need to look at a generalized case. Generalize what is the meaning of this x dot is equal to j into theta dot. Okay, now so far we assumed that j is equal to m into m, which is a square matrix. Okay, but now let us say that j is not square. Then what happens? So let us say that I have a 3 degree of freedom manipulator like this. So there is 1, 2 and 3. This is my xy. Sorry, that's my xy. So in this case, j is equal to 2 into 3. And the generalized solution of this equation, j into theta dot is equal to j hash x dot plus j hash j minus I into lambda. This is the general solution of matrix inversion, where j hash is called the pseudo inverse. Okay, and this is a positive constant. Okay, so this is the generalized solution where your matrix j is non-square. Okay. Now we'll come to this, we'll come to pseudo inverses, but let us try to understand what is the meaning of now what is the matrix actually, what is the mechanism of a linear operator. And we'll also have to talk about singular value decomposition. You might have heard of eigenvalues. Okay, you have heard of eigenvalues. So what is the geometrical interpretation of eigenvalues? So we said eigenvalues, we talk of eigenvectors. So what is the geometrical interpretation of this? That is something we'll have to look at. Now, eigenvalues are only for square matrices, m into m. We want to talk about a generalized case, m into n, where it is not a square matrix. Then what do we talk about? Okay, so let's start off this rather new topic. You may not be familiar with this, but this is extremely important for us because in robotics, j can become non-square. J can be square, it can be non-square also. Okay, so we need to find. So singular value decomposition in short called SVD, singular value decomposition of a matrix, SVD of A, is breaking this matrix up into 3 matrices, U, sigma and Vt, in which case U and Vt are orthogonal matrices. Okay, and sigma, which comes out to be, which is a diagonal matrix up to sigma n, this is called the it is a diagonal matrix. This is a diagonal matrix. Okay, so we are breaking this matrix up into 3 parts, any matrix into 3 parts. The first part, this is U, sigma and Vt. Sigma will have this is a diagonal matrix consisting of the singular values, where sigma 1 up to sigma n are called the singular values. Okay, now what is the geometrical interpretation of this? So singular value decomposition is basically ordering a system. What we can say is that when we have or reducing the dimensions, so basically what we are doing is, for example, you would have done this example. So you have a number of points and you're fitting a straight line. So it is a dimension reduction going on. You have x and y in which there are points. What you're doing, you're fitting the best straight line which has the shortest distance from this. So what you're trying to find is, this is x and y had 2 dimensions, right? It was 2, but the straight line has only 1. Okay, so you're reducing that to 1 dimension only. Right? So it is a kind of a dimension reduction which is going on. Okay, or trying to find the direction in which there is maximum variation in the data points. Okay, now that sounds a little bit, let me explain it a little bit more clearly. So when you have So what we're trying to do is we are trying to look at this equation x dot is equal to j into theta dot. We're trying to understand what j is doing. Okay, now this is similar to this equation you would have studied, y is equal to x. So the same question comes, what is a doing? Okay, so this is what we call, let us try and understand this as a mechanism of a linear operator. Okay, so a matrix here, this matrix A, so matrix A or J. Okay, so matrix A or J, as I wrote above, okay, is can be regarded so it can be regarded as the implementation of a linear operator. Okay, so a matrix here, this is a matrix. This can be regarded as a linear, it can be regarded as the implementation of a linear operator. And we are looking at the mechanism of a linear operator. That means what does it do? In the case of the robot, it's very, very important because we are talking about a physical system. And this is just not maths, but this is a physical system in which we have theta 1, theta 2, xy, and we have x dot is equal to j into theta dot. So what is this x doing to that joint velocity? Okay, that is what we're trying to answer here. Okay, so now if you look at that and we think about what it does, we can understand it this way. This transformation, what it does is, so I had SVD of A. I broken up into three matrices, which is U sigma, and VT. Okay, what does this mean? This means that I'm trying to look at what is this equation y is equal to ax, what is A doing there. Okay, so it is similar to saying that I have my system, okay, in case of our velocities. Okay, this is v1, v2 and vn. Okay, now suppose I say that the input is constrained in a unit sphere. Okay, this is a unit sphere, equivalent x dot. Okay, now suppose I say that your input velocities are constrained in a unit sphere. Okay, then what is this operator doing? Or sorry, it's the other way around, I did not write it correctly. X dot is equal to j into theta dot. Okay, so what is this operator j doing? Okay, this is my unit sphere theta dot. Now what is this operator A doing? It is taking some of the velocities, scaling it and rotating it. Okay, so it is scaling and it is rotating. So my rotated system will become something like this. This will become my u. So this is my u1, this is my u2. Okay, and this could be u3, and the other side is u3. So it is taking this unit sphere and it is scaling it and it's rotating it. So this unit sphere has become an ellipse now. Okay, so what is going on is that this unit sphere is being scaled. It is being scaled by what? It is being scaled by the sigma 1, sigma 2 up to sigma n. Okay, this is my sigma 1 and that is my sigma n. And it is being, first thing is being scaled, number 2 it is being rotated. Okay, so the initial axis was v raised to t, rotated system is u. Okay, so what does this matrix do? So the matrix is an implementation of a linear operator. So this fellow y or this fellow j, what it is doing is it is taking the input of the joint angle velocities, scaling them and rotating the axis and putting making that the end effector velocity. Okay, that is what it is showing. So here this is my unit sphere. How do we get a unit sphere? So if I normalize all the joint velocities, then they'll become less than or equal to 1, and that's a unit sphere. Okay, so what is this operator J doing? It is scaling this unit sphere and making it into an ellipsoid. So this is a sphere, it's a unit sphere, and this is what we call an ellipsoid in n-dimensional space. Okay, now seems a little abstract, but this is what a matrix actually does. A matrix is a linear operator, and what it does, it takes that x, scales it, and rotates it. Okay, so if this is my input unit sphere, the output is an ellipsoid. What does this mean? Now, what does this mean? Let us look in terms of robotics. It basically means that if this is my motor, I'm giving some voltage, I'm giving some theta dot, theta 1 dot, theta 2 dot. Okay, so this is my unit. So theta 1 dot and theta 2 dot, my input is theta dot. So that's my unit sphere. And if I normalize it, then this can be mod of that can be less than or equal to 1, which is a sphere. This is my V1, V2. Okay, this is the axis. So my input velocities are contained within the unit sphere. What is the output? The output is, so what would this matrix J do? It will scale and it will rotate. So if it is scaling, it is taking each of these axes here. They are equal because it's a sphere. So what it is doing is it is scaling and it's changing the axis direction. Okay, so it is scaling it and making it like this. And this is my U and that's my V. This is my U1, U2. Okay, this is my sigma 1 and this is my sigma n. In this case, it's sigma 1 and sigma 2. Okay, so what does this mean? My input was a unit sphere, but my output is an ellipse. This is what it means. Okay, now what is the indication of sigma 1 and sigma 2 in this case? Sigma, the ellipse gives the direction in which you can move easily. So this ellipsoid gives directions in space. So ellipsoid gives directions in space in which you can move easily. Okay, so you can move very easily towards sigma 1. So sigma 1 means easy motion. Okay, and sigma n, the last one, will mean difficult motion, difficult or not possible motion. Okay, this is what it means. And what is the direction? The direction is given by the vector u. So u is the one, the orthonormal basis or the orthonormal matrix U. The columns of that are the axis actually, and that is the one that is giving you the direction. Okay, so let me look at it here. So this basically means, in the figure I've drawn here, you can move easily in this direction. Okay, you cannot move easily in that direction because the ellipsoid is like this. Okay, let's go back to the example I was giving in the beginning of the class today, that you have a 2 degree of freedom manipulator. Okay, when it becomes in a singular configuration here, this singular, this is not singular. Okay, so here at the boundary singularity, what is happening is that it is losing rank. It's a 2 by 2 matrix. Here J is equal to 2 by 2. Okay, so what is happening here is that your determinant of J is becoming 0 because it's a singularity there now. Okay, sine theta 2 is becoming 0 because theta 2 is 0 now, and that's my theta 2, right? So we are at a boundary singularity. Now at that boundary singularity, what is happening is the ellipsoid, if I draw the ellipsoid here, okay, if I take the singular value decomposition of J, so if I do SVDJ, I'll be getting U sigma Vt. Okay, U is going to give me the axis of the ellipsoid. Okay, and so U is giving me the axis of the ellipsoid. This is giving me the magnitude of ellipsoid. Okay, sigma 1 and sigma 2. Now in this case, you'll find that there what happens, it becomes a straight line. So this ellipsoid is changing direction. Is changing the shape. So ellipse is changing shape. Now straight line means what? One of the sigmas, sigma 2, has become 0. That means it cannot move in this side. Whereas sigma 1 will have some value, which means it can move in that side. Okay, so in this configuration, if I find the Jacobian, I find the singular values, what will happen is for these values of theta 1 and theta 2 equal to 90, what will happen? Your sigma 2 will become 0 and you'll only have sigma 1, which means that your ellipsoid is becoming a straight line, and you can move upward and downward, but you cannot move towards the body because one of the velocity vectors has become 0 now. Okay. Now, when you're somewhere in the center of the workspace, if I draw the ellipsoid, your ellipsoid will become a circle here. So a circle basically means sigmas are equal. That means sigma 1 is equal to sigma 2. This means that an ellipse has become a circle. So if I look back and see what this operator is doing, or here, for it is a sphere, and this sphere is being squeezed and being rotated at the same time. Okay, so it is changing direction. So if your sigma 1 is equal to sigma 2 is equal to sigma 3 is equal to sigma n, they are equal, then it means that it's a sphere. Okay, what does that mean? It means you can move equally in all directions. That is in the center of the workspace. Whereas if you're going near a singularity, what will happen? Some of the singular values, some sigmas will become 0. Okay, or it will become very, very small. Okay, so will become small. If they become small, it basically means that your circle is now becoming an ellipse like this, thinner, and then finally it becomes a straight line. Okay, so at the boundary it is this, in the center of the workspace it is this. Okay, so and as you're moving in space, what is happening? Your ability to move in different directions is getting reduced. Okay, it depends on the singular values now. So that is basically what is telling us that why when we are moving from here to there, your determinant of j was equal to 0, which means you are at a singularity, whereas here you're in the best position because your determinant of j was equal to 1, L1, L2 equal to 1. Okay, so this gives you a better understanding of when we are moving in space, what are the directions in which we can move easily and which are the directions which we cannot move easily. Now, the directions obviously in which you cannot move easily, those are directions which you require maximum energy also. So this gives us a very, very important relationship, or it tells us something about what Jacobian is doing. So Jacobian is a matrix and it is behaving like a linear operator. So in any equation y is equal to ax, this is what a is doing. In our case, this is what j is doing. Okay. So it's interesting that when you look at the linear operator, what j is doing is it is taking the joint velocities, okay, squeezing them and then changing their axis, because of which the end effector is always becoming a ellipse. This is something very, very interesting, that your joint velocities can be a sphere, but your end effector velocity will be an ellipse. Okay, so if you try drawing a circle, okay, please try drawing a circle sometime, you'll find that it becomes an ellipse, exactly because of this only, because from our joint velocities, theta dot is equal to j into x dot. This is your end effector velocity or your hand velocity, and this fellow, what it does, it scales and it turns, so it makes a sphere. If you squeeze a sphere, it becomes an ellipse or an ellipsoid. That's what it is doing. Okay, so whenever you try to draw a circle, you'll find that you end up with an ellipse. Okay, and this is the reason why. Now we need to understand the singular value decomposition very well, because this is where we are going to proceed from here, and it's very important for us to understand this, because we also need to understand we need to understand about the matrix inverse for non-square matrices. Okay, because in robotics that is important. So let's look a little bit into singular value decomposition as we proceed, and then we'll also look at pseudo inverses, how to invert matrices. Now we talked about a determinant of j, and our j was given by minus L1 sine 1 minus L2 sine 1 2 minus L2 sine 1 2, and here it was L1 cos 1 plus L2 cos 1 2 L2 cos 1 2. Okay, this was our Jacobian, and we said the determinant was L1 L2 sine 2. Okay, now what about a non-square matrix? What about its determinant? Okay. Now we can also find the determinant of J by finding the eigenvalues E1 and E2. Okay, so the determinant is also equal to the product of the eigenvalues. Okay, so this is another way of finding the determinant without doing this. You find the eigenvalues and find the product of the eigenvalues. That is a determinant. Okay, so that means there is a relationship between the eigenvalues in the case of a square matrix and the determinant. Okay, what are we trying to do? We're trying to understand that when determinant is changing, as we are moving in space, the determinant is changing, right? So what does it have to do with the eigenvalues of the matrix? So the eigenvalues are similar to the singular values. We talk eigenvalues of a square matrix, we say singular values of a non-square, it can be of any matrix. Okay, so we talk of singular values, okay, as a general case for any matrix. Okay, so J can be square, it can be non-square, it doesn't matter. Okay, now let us look at how do you find the singular values of a non-square matrix. Okay, so what we're trying to do next is find singular values of a matrix. Now this matrix can be square, it can be non-square, it doesn't matter. Okay, then we'll try and find the relation between singular value, then between eigenvalue, then we have to talk about, so what we are doing is we're taking this matrix J, or we can talk about the matrix A, any matrix A, SVD of A is equal to U sigma VT. Okay, this is going to give me the singular value sigma 1 up to sigma n, and U and V are the orthonormal matrices. Now why do I need to do this? Because when my manipulator is moving, let's consider this manipulator here. Okay, this is my manipulator which is moving. It has some end effector velocity x dot y dot. So if I give some theta dot, I need to know what is going to be my x dot and y dot. That depends where you are in the workspace, because your Jacobian is going to change accordingly. And the direction in which I can move is given by the ellipsoid now. And this ellipsoid axis is given by U1, U2, and it is given by sigma 1 and sigma n here. Okay, so the shortest one will be sigma n. It is ordered in that direction. Singular values are ordered from sigma 1 is greater than sigma 2 is greater than sigma 3 up to like that greater than sigma n. So this is the largest, that's the smallest, and that's the way it is ordered. Okay, so depending on that, we need to find out which direction in space can you move and which direction you cannot move. Okay, so we need to find the singular values, and in the process we'll also find what is matrix inversion, what is the determinant, and you'll be surprised that a lot of the programs like MATLAB, when they find matrix inversion, they don't do adjoint of matrix by determinant of matrix. They don't solve it like that. They solve it by finding singular values, okay, because this is more generalized. Okay, so let's proceed. Let's take an example of finding singular values of this matrix. So let's say we have a matrix A. Okay, I want to find SVD of A, which is given by U sigma VT. Okay, so let me take a numerical example. A is equal to, let's say 4, 0, 3 and minus 5. Okay, this is my matrix A. I can take the transpose of that, which is equal to 4, 3, 0 and minus 5. Just I've taken it for simplicity, it's 2 by 2 and it's a square matrix. It can be any matrix, it can be non-square or square. Then I take A transpose, which is equal to, if I multiply A into A transpose, I get 16, 12, okay, 12, 34. Why do I do this? Because if A is non-square, A is M into N, then if you do A into A transpose, it will become square. I hope you understand why this was done. So either it is A transpose or you can do A transpose A. It's the same thing, it doesn't matter. Okay, so A transpose is equal to 25 minus 15 minus 15 and 25. So we are basically doing this operation and this operation to convert a non-square matrix. So a non-square matrix is being converted to a square matrix. Okay, so what we have done is we have found now what is the determinant of so determinant of A is equal to minus 20. Okay, so this is equal to minus 20, determinant of A. What is the determinant of A transpose? Determinant of A transpose is equal to determinant of A transpose A, which is equal to 400. So mod of this is 20. Okay, so something interesting to note is that square root of determinant of A transpose is equal to determinant of A. Okay, that's what we're seeing here. Okay, so mod of this, yeah. So this is interesting to note that these determinants are equivalent. Okay, next what we do is we find the characteristic equation. I want to find the eigenvalues. Okay, so I want to find the eigenvalues of I want to find the eigenvalues of A and A transpose A. Okay, so the characteristic equation of the matrix A is equal to c squared plus c minus 20 equal to 0. Okay, which means that the eigenvalues c1 is equal to 4 and c2 is equal to 5. This is the eigenvalues. You know how to find them, right? Now what about the characteristic equation of A transpose and A transpose A? It's equal to c squared minus 50c plus 400 is equal to 0. So that gives us the two eigenvalues. c1 is equal to 40 and c2 is equal to 10. Okay, now we talked about the determinant of A. So determinant of A is equal to now c1 into c2, which is equal to 4 into 5, which is 20. Similarly, determinant of A transpose is equal to determinant of A transpose A, which is equal to 40 into 10, which is 400, and that is exactly what we had got here. Okay, so when you find the determinant in the normal procedure, that is rows into columns, then we got determinant of A to be 20 and determinant of A transpose to be 400. So it basically means that you can find the determinant from the eigenvalues also. Okay, so this is what I'm trying to find, the physical meaning of the eigenvalues. What does it mean? It basically means that the eigenvalues are going to scale your unit sphere and is going to rotate. So first of all, it is going to scale, and your orthogonal matrices U are the ones that is going to rotate. Okay, so that is what it is doing, and that is what I'm trying to find out, and trying to find the relation between eigenvalues and then proceed. Okay, so this is giving us the characteristic equation for the eigenvalues for the matrices A and A transpose and A transpose A. Now I want to find the eigenvectors. Okay, so now we have found the eigenvalues. So what we can do is computing sigma matrix can be found by taking C1 greater than C2 greater than C3 in that order. Okay, in this order we put, and then taking their square roots of non-zero. So singular values equal to square root of non-zero eigenvalues. Okay, so what are the singular values? The singular values are the square roots of the non-zero eigenvalues of the matrix A transpose A or A transpose is the same. Okay, so either this one or this one, the eigenvalues are the same. So the square root of the eigenvalues, non-zero eigenvalues, is equal to the singular values, and you have to order it this way such that it comes in the order that sigma 1 is the largest, then sigma 2 and sigma n is the last. Okay, so sigma 1 is greater than sigma 2 greater than sigma n. Okay, so this is how we get our sigma matrix, the diagonal matrix. Now the singular values are the ones that are going to scale the velocities. So we also need the directions u and vt. Okay, so in this particular case, the example that we have got, we have two eigenvalues, right? We have got eigenvalue here 40 and 10. Okay, so what are the two eigenvalues? What are the two singular values? Sigma 1 is equal to square root of 40, which is equal to 6.32, and sigma 2 is equal to square root of 10, which is equal to 3.16. Okay, and the determinant of A transpose is equal to sigma 1 into sigma 2. Okay, so remember I started off by saying that we said the determinant is a metric, and the value of the determinant changes as you start going towards a singularity, you come away from a singularity. So if you're trying to find the determinant of a large matrix, say it's a 6 by 10 matrix for a 6 degree of freedom, for a 10 degree of freedom system. So it's difficult to find. You cannot find it in the normal way. So the determinant is simply the product of the singular values. Okay, that's how we find the determinant. So another point, we talked about eigenvalues. Okay, then we talked about singular values. We also talk about the rank of a matrix. So what is the rank of a matrix? So the rank of a matrix is equal to number of non-zero singular values. Okay, so if your determinant is like this and one of the singular values were to become 0, then obviously it is losing rank. Okay, so in a singularity, what is happening? Your system is losing rank now. The matrix J is losing rank. This is what it means. So in this particular case, our singular sigma matrix is equal to 6.3200 Okay, this is my sigma matrix. I next need to find u and vt, because I need directions in space, because I need the directions in which it can move, right? I know the magnitude of the ellipse. So the ellipse that I'm going to draw here, or the ellipsoid that I'm going to draw, will be like this. Okay, so this is going to be my 6.32, that's my sigma 1, and the other side is going to become 3.16. they're not equal, so it's an ellipse. Okay, now I need the directions. Where is the u direction? Okay, because I need the direction of the ellipsoid also. So for doing that, what we do is so I need to find the eigenvectors, characteristic equation, and the eigenvalues of A transpose. So from here, after finding the eigenvalues, I find the eigenvectors. Okay, we find the eigenvectors by using this equation: A minus C into I into X, xi is equal to 0. You know how to find eigenvectors given the eigenvalues. So for C1, equal to 40, okay, we find A transpose A minus C into I is equal to, so I'll write it as 25 minus 40 minus 15, that is minus 15. This is 25 minus 40. Okay, so this comes out to be, so this comes out as minus 15 minus 15, and we have minus 15 and minus 15. Okay, and x1 x2 is equal to 0. So what I do is I'm using this equation. Okay, so what I'm doing is I'm getting these two equations from here. I get two equations, minus 15, and so from here I get two equations, right? So minus 15 into x1 plus minus 15 into x2 is equal to 0, and the other equation that I get, minus 15 into x1 plus minus 15 into x2 is equal to 0. Now solving for x2, we basically get x1 is equal to, or x2 is equal to minus of x1. That's what we get from these two set of equations, right? So x1 is equal to x1 and x2 is 1 is equal to x1 minus x1. Okay, so dividing by the len, normalizing. So next what we do is normalizing it. how do we normalize? We normalize it by L is equal to dividing it by x1 squared and x2 squared. I normalize it and I get x1 is equal x1 root 2. Okay, so what we get is we divide all of this x1 by, so I divide x1 and minus x1 by L, and what we get is we get the normalized value, which is 0.7071, and this is minus 0.7071. Okay, so this is what we get now. So this is for eigenvalue equal to 40. Now I have another eigenvalue for which I have to find the eigenvector. So for this one, for C2 equal to 10, okay, we can get the eigenvectors to compute exactly the same way eigenvectors, compute the eigenvectors, and what we get is x2, so I can write A transpose A minus C into I is equal to 25 minus 10, eigenvalue is 10 now, minus 15 and 25 minus 10, okay, which is equal to 15 minus 15 and 15. Okay, so solving this set of equations, we get x2 is equal to x1 x2, which is equal to x1. Now what we get, we normalize. If we normalize, then L is equal to x1 root over, we are normalizing, so x1 squared plus x2 squared, square root of this, which comes out to become x1 root 2, exactly same as before. So my second one is equal to x1 by L, and this is also x1 by L, so it becomes 0.7071 and 0.7071. Okay, now I take these two columns and I make my V vector, the orthogonal matrix. V is equal to 0.7071. This corresponds to eigenvalue C1, and minus 0.7071. This corresponds to eigenvalue C2, which is equal to 0.7071 and 0.7071. Okay, so this is my V. So if I take the transpose of V, what I get is 0.7071, and this is 0.7071, and here it is minus, and to 0.7071. Okay, so I've got my VT. Okay, that is what was the direction of the axis before rotation. Okay, now to get the axis after rotation, I need to find which is U. Okay, so after rotation we need to find U. So I need to find, next we need to find U, because remember that SVD of A was equal to U sigma VT. Okay, so I have found sigma, I have found VT, I need to find U. Okay, so now from this equation, A is equal to U sigma VT, what I can do is A into VT, I bring it this side. Okay, into inverse of this is so U and V are orthogonal matrices. That means V transpose is equal to V inverse. Okay, so I get this from this equation, I get this. Now from this equation I get this now is equal to U of sigma. Okay, so I get U of sigma here, and then further I'm looking for U. So what I do, I bring U here. U is equal to A V into sigma inverse. Okay, so this fellow I bring him this side now. So U, I know what is A matrix, I know what is V matrix, and I also have found sigma matrix. So what I do is I simply multiply them out now. I get my sigma, I know what is sigma. Now sigma inverse, we have found sigma. So sigma inverse is equal to 1 by sigma 1. This is 0, this is 0, 1 by sigma 2. Okay, so which becomes equal to, so this is equal to 0.3162. Now I multiply U is equal to A sigma V inverse. I just put the matrices in, okay, and I multiply them out. So what we get is u is equal to, please put the matrices A, V and sigma we have just done. So this becomes 0.4472 and this is 0.8944. This is 0.8944 and this is minus 0.4472. Okay, this is the left, this is u. So I have found u, I have found sigma, I have found Vt. Okay, so for any matrix A, I now know what is sigma, how it has been scaled. Then I know what is the direction in which it was before scaling, and I know the direction it was in after scaling. Okay, so this will enable us to know that when we have a transformation x dot is equal to j into theta dot, okay, then for given velocities, I'm going to, it can be any degree of freedom manipulator. I'm giving some joint velocities here, theta 1 dot, theta 2 dot, theta 3 dot, okay, theta 4 dot. Now what is the direction in which the end effector can move easily and the direction in which it cannot move easily? So for example, the ellipsoid can become like this. Okay, I need to know what is the sigma, what is the sigma 1 and what is the sigma n. Okay, in terms of a metric, we said the metric of half of manipulation ability W is equal to the determinant of this j, whatever is the j here. Okay, so determinant of j, and in case of a redundant manipulator like this, it is determinant of j transpose. So this is, so what is determinant of j? It is the product of the singular values, sigma 1 into sigma 2 into sigma n. Okay, so now we have a metric. So sigma 1 into sigma 2 into sigma n is the determinant of the matrix. Now this is independent of whether matrix is square or non-square. Okay, so if it's a square matrix, it's easy, you can find it this. If it's non-square, is the same thing, singular values can be found, and we know the determinant now. So the determinant is the metric of the direction in which you can move easily and the direction in which you cannot move easily. And that's very, very important, because when we are moving, your energy consumption depends on this now. Okay, today we looked at the singular value decomposition, and we also looked at the actual transformation that happens between the joint velocities and the end effector velocities. And we saw that if the joint velocities are contained in a unit sphere, then the end effector velocity is contained in a hyperellipsoid. And in this case, your Jacobian matrix basically behaves like a linear operator. In the next class, we'll have to prove that if your input velocity is a sphere, the output is actually an ellipsoid. Okay, and then how do we use this in our further study? So we'll stop today. Thank you.